Evolutionists, why does your evidence suck so bad? I've been asking for evidence for evolution, and so far it's been, I'd say, close to zero. And in this video, I'm going to start by just sharing some of the most recent evidence that has been presented for evolution when I do this on my channel. Then after that, I'll give an opportunity. If you want to share your evidence, you can join, although there's already somebody waiting backstage and I'm only letting one person on at a time now. So I'm just going to share, so you may have to wait if you want to join, but I'm going to share some of the evidence that was shared last week and talk about why it is not at all evidence for evolution. So Howard shared that there was an evolutionist who predicted basically the similarity genetically between echinoderms and chordates. And so this was back in 1908, Carl Groban. And you know, when I looked into this, at first I granted it to Howard as a weak prediction, but then I read a little more and I was like, wait a minute, all he did was look at a developmental similarity between echinoderms and chordates. And so he saw that developmental similarity and he grouped them together. Now, that it wasn't actually a prediction that they would be genetically similar, but is it even a surprise that organisms that are morphologically have and developmentally share similarities would also share genetic similarities? So this is not any prediction of evolution, and it's not evidence for evolution. Just being able to group animals together by similarities does not show that they developed from a common ancestor over millions of years. The other thing that Howard brought up, and I already sort of responded to this, but I wanted to talk about it a little more because he keeps bringing up that there are certain types of animals not found in certain layers. Now, that is not evidence for evolution. He brought up, oh, why aren't there any bears in the Cambrian? Okay, well, I don't know, but that's not evidence for evolution. It might be evidence against some sort of idea about creation, but it's not positive evidence for evolution. Actually, it's problematic for evolution because we don't have anything leading up to the bears. We have the sudden appearance of bears and the sudden appearance of many forms. In fact, that is what is really the fossil record. Throughout the fossil record, we have the sudden appearance of forms. So Howard also said, why are there no plants in the pre-Cambrian? Well, again, that is not positive evidence for evolution. Actually, there's a problem with plants because they suddenly appear in their forms in the fossil record. So we don't have what we would expect if evolution is true, which is a long progression of development of these various type of organisms. Okay, Mirsa brought up onions have a large genome. Now, I don't know why this would be evidence for evolution, okay? It's certainly interesting that onions have a bigger genome than, for example, humans. And in fact, there's something called the C-value paradox, which is that, hey, we seem to see no connection between organismal complexity and the size of genome. But does that supply evidence for evolution? That it's unclear how that would. So just observing that onions have a larger genome does not tell us that they developed over millions of years. And in fact, there's a problem with onions because, again, onions appear suddenly in the fossil record. I mean, I don't even think we have a fossil record of onions. So where's the development of onions? And so it's actually not evidence for evolution. Finally, Howard had a problem with what I put up here about my evidence against evolution. I give 4 reasons to reject evolution. And he had a problem with the first one that I said, that the proposed mechanisms for evolution are grossly insufficient for producing the diversity of life on Earth today that we see today. Now, he picked on that and he said, wait a minute, we don't need a mechanism in order to know that evolution, happened. We don't have to have a mechanism. And one thing he cited was, plate tectonics, that, this was proposed that the continents had moved apart, and it was proposed way back when with the idea of continental drift. And he said, we didn't know how it happened, but hey, it doesn't matter because it did happen, and we eventually figured it out. And my response is that, well, but we don't just accept something unless we have the evidence. And even though when I forget the guy's name, Alfred Wegener proposed continental drift, it was actually rejected by the scientific community, even though there were some evidences for it. But there was no mechanism, and it wasn't actually accepted until we found the mechanism. So there's other mechanisms. I mean, there's other examples that Howard gave me by email, which is like, oh, we didn't understand gravity, but we still were able to, believe that the planets were in motion and stuff like that. And so my response is that, yeah, but we actually could observe the planets in motion. So my complaint is that we don't have the evidence for evolution. So it's a huge problem that our proposed mechanisms are grossly insufficient. Because if we're going to call this a scientific theory, then we should have scientific evidence to back it up. Now, it's not saying we have to have every detail worked out. Maybe we could if we had just an abundance of evidence, not fully understand the mechanism, but we don't have that. And that's a problem. And so now I'm going to let on my guest, but I think that is all the evidence that was brought to me so far. Just to recap, the only person who has brought evidence that actually stuck for evolution is Grayson. So Grayson is the only person so far that brought evidence, and he brought the 2 predictions that evolutionists made about finding types of transitional animals. He gave Archaeopteryx and Tiktaalik as, these look like what evolutionists expected to find. And I admit that they have sort of some features that we could say belong to both, for Tiktaalik, amphibians and fish, and for birds and reptiles, we could say Archaeopteryx shares features. So I would say that was a good prediction of evolution, and it's the only evidence so far that anyone has brought that has stuck. And so let's see if our first guest can bring some real scientific evidence for evolution. And I actually have high hopes for this guest, because we have Erika from Guts and Gibbon. So welcome, Erika. Good to see you.
Hey, Rebecca. Good to be here. Yeah, I hope I can join the list with Grayson for you today. We're going to be talking. I said this in the side chat, but I think the topics that you've already discussed lend themselves very well to what I would like to discuss today, because I'm talking about transitional species, right? I'm going to be talking about the fossil record, transitional species, how that bears on predictions that were made previously, and why I think, and I'm biased, why I shouldn't say that it's the best support for evolution, because I don't think it is, but it's my favorite. And I think it demonstrates it better than a lot of things, just because of how intuitive it is. So I'm excited to talk about that.
Cool. Thank you. And for others backstage, I just want you to know it might be a little while. So you can wait if you want to, but I'm going to give Erika as much time as she wants to discuss her evidence.
Should we just get into it?
Yeah, let's do it.
Yeah, cool. Okay. Now I actually have pulled up a PowerPoint that I used in my recent debate with Jerry Bergman a little while back, so we can consult it if we need to and look at the actual bones, because this is going to be one of those things that it's because we're talking fossils, you got to see them. I mean, you got to look at them to know what they mean, and we have to make these kinds of comparisons. So here's my case. I'm going to make it really simply. Evolution since Charles Darwin predicts morphologic or physical change over geologic time. That means that if humans evolved from a more basal ape and this is something we can discuss as well, but humans are physically apes. I don't think that that's going to be controversial. It's not with Sal. I've discussed this with Sal before, and Sal is fine. Insofar as you can categorize organisms. I mean, goodness, this was recognized by Linnaeus, who existed and categorized humans with other apes before evolution was ever proposed by over 100 years. No, maybe not over 100 years, by around 100 years, let's say, in the 1700s. Anyway, so if humans evolved from a more basal ape, though, and this isn't a common design thing, but it is the result of common descent, then we should see one thing, and we should see it abundantly clearly. We should see the emergence of the characteristics that make humans human emerge slowly over geologic time from more basal apes that are just like living in the Miocene approximately 7+ million years ago. So my case is that not only do we see this, but we see this in absolute spades. We see absolutely every characteristic that makes humans human emerge slowly through geologic time, and that these hominins are well represented in the fossil record. So what I'll say is that that's where I think we'll start, and then I'll probably share my screen and we can walk through some of these fossils.
Sounds good.
Cool. Do you have anything you want to like?
Monkey look kind of like a person. Monkey look kind of like a person. Monkey
That's true.
That's all I got to say.
Monkey look kind of like a person.
That's,
go on.
I mean, that's the case I'm making though. And again, like before, actually, I guess I should say this before we get started. I don't think it's controversial to say that this was predicted, right? Like this was outright discussed by Charles Darwin, that we should see these ape men. In fact, Darwin proposed that we would find them in Africa. And the reason he proposed that we would find them in Africa isn't because we'd found any hominin fossils in Africa. He proposed it because that's where chimps and gorillas live now. So he was like, if non-human apes still live in Africa, that's probably where humans evolved. And this was the sort of basis of his opinion. This was pushed back against by the likes of like Ernst Haeckel, who were like, yeah, but you also find non-human apes in Southeast Asia in the form of orangutans and gibbons. And, his idea threw everybody off of the scent for a little while. But that being said, let me find my window here, Chrome tab window. All right. Can you see that? Cool. Okay. What I'm going to do is I'm going to not click the present on this just because I don't know how to do it in a way that's going to like not mess things up here. But this was from the debate that I had with Jerry Bergman. He's a young Earth creationist, and we're not going to discuss like age of the Earth stuff today because I think we can agree at the very least, I hope we can agree at the very least, that the order of the fossil record is at least relatively reliable in the sense that things that are lower were put down before things that are higher, right? Like we don't have to say how long ago it was, but it's like stuff that's low down was deposited before stuff that's high up. So under either expectation, right, we should see this emergence through time. So I'm going to hit you with a term just so you know what I'm talking about here.
Okay.
A hominin, which is what I'm going to be talking about for the case of human evolution, is just anything that's more closely related to a human after the split with chimpanzees. So under evolutionary theory, right, genetically, humans and chimps are more similar to one another than chimps or humans are to any other ape, right? So humans share more genetically with chimps. Everybody knows that. But chimps also share more genetically with humans than they do with gorillas or orangutans or gibbons, which I've not ever heard a common design explanation for, but let's set that aside for now. So hominins are going to be any of those fossil apes that fall on the human side of things, as opposed to the chimpanzee side of things. That's what a hominin is. On the sort of other side of that would be panins, because chimpanzees, the genus is called Pan. So as I said with Jerry, these fossils exist. We have a lot of hominin fossils or ostensibly apey looking fossils. How do we actually interpret them? Because we have these same data. We're all looking at the same crania, as many creationists often like to say. So it's like, what do we do with these crania? How do we actually interpret them? And evolutionary theory would say humans descend from more basal or primitive apes. So the hypothesis is fossil hominins are all close human relatives. So all of those skulls that we find, if they are on the hominin side of things, then they're close human relatives. And they should have these characteristics, as I said at the top, that emerge slowly over geologic time. So in a second, I'm going to tell you, like, okay, what are those characteristics? But I will say that there are other predictions that this hypothesis makes. Like, it also predicted that humans should have all of the morphologic characteristics that define other living apes. People can say that common design is another explanation for this, but I already talked a little bit about, which is the second point here, the reason why I don't think that that works. And that's because humans should be more genetically similar to the other apes, but there's no reason why humans and chimpanzees share more genetically with each other as compared to a gorilla, given what we all look like, right? Like, I don't think if you put a chimp, a human, and a gorilla in front of like a toddler and you were like, pick the odd man out, that they're going to pick the gorilla. But genetically speaking, we share more with chimps and they with us than either of us do with gorillas. That would be an evolutionary prediction because the two of us are a part of the same sister taxa, where we're two sister taxa as compared to the gorilla, who is the outgroup.
Well, let me ask you this. If
Yeah,
it
please.
turned out that gorillas were more similar to chimps than chimps are to us, would that be a falsification? Would that go against evolutionary theory?
I don't think so. I think it would depend on the means by which they are, right? Like, it's hard to say. Well, actually, so I'll say it this way. No, it wouldn't, because historically that's what we thought until we started doing the first sequencing, right? Like, everybody thought, and this is why historically, and you can go back and read some old like anthropology books and papers on this. I have to do it all the time for school, but it's like, you may remember that we used to call human relatives in the fossil record hominids, IDS, instead of hominins. And the reason for that is that humans and our relatives used to be all in our own family called hominidae, whereas chimps, gorillas, and orangutans used to be in their own family called pongidae, right? The only reason why everybody is now a hominid is because when we started sequencing their genomes in like the latter half of the 1900s, it turned out that humans and chimps shared more than gorillas and chimps did, which didn't make a lot of sense, again, because gorillas and chimps ostensibly look more similar than either of them does to a human. So no, it would not falsify evolution. This was a surprise from an evolutionary perspective because of how they look. Does that answer your question?
Okay, well, so then how can it be supplied as evidence for evolution if no matter what we find, well, first you just admitted it was a surprise for evolution, so it wasn't an evolutionary prediction, but if you're saying no matter what we found, if gorillas were more similar to chimps, that would be also fine for evolution, then how does the chimp human similarity actually weigh as evidence for evolution?
Because the idea was originally, like, the argument between creationists and evolutionists back in the 1900s was, are humans apes or not? Right? Like, because we should nest outside of the other apes if we're not apes, or at the very least, we should be a different group. So everybody expected, on the basis of the physical similarities, that humans were apes, and creationists sort of railed against this, but they maintained that we were sort of a separate kind of ape because of how this family tree worked. But because it turned out that humans and chimpanzees were more closely related, it means that you can't actually group all the other apes together without necessarily including humans. So it's not that it matters that it is a prediction that humans are close to apes. It matters that humans are more close to chimps and that chimps are more close to humans. Does that make sense?
Well, I mean, what you're saying makes sense, but it doesn't give me a reason to think this is evidence for evolution. So, and we can label something anything we want. It doesn't mean they developed from a common ancestor. So, if you want to group these similarities together and say humans share enough similarities with these apes that we're going to call them apes, okay, that's just putting a label on something.
Sure.
That doesn't say it developed from.
I understand where you're coming from. The reason this is important for this conversation is because creationists, historically speaking, used to say, beyond a shadow of a doubt, that all the apes come from a common ancestor and that humans aren't apes. Now, if that's the case, like, even taking your more progressive creationist perspective that humans are technically apes, but we don't all share a common ancestor. If all the other apes come from the same kind, you can't have humans and chimpanzees be more closely related to one another than either is to a gorilla, right? All three of those guys should be kind of like a family tree. This would be like proposing that me, my sister, and my cousins, you want to say that my sister and my cousin are more closely related than I am to my sister. You see what I'm saying? So necessarily, because chimpanzees and humans share more than either does with a gorilla, they have to stay attached as sister taxa, in the same way that me, my sister versus all my cousins have to stay attached because of our genetic similarity. So what this means is that from a creationist perspective, you have to propose that either gorillas, orangutans, chimpanzees, and humans, all four have a separate ancestor and none of them are related at all, or they are all related to one another, because humans and chimps of those four are the most genetically similar.
Okay, well, again, it's only what you're doing is grouping things together and naming them. So that isn't showing development from a common ancestor.
Do you think that, can you say the same for me and my sister versus me and my cousins?
No,
Why?
I wouldn't say the same, because I mean, obviously have a shared ancestry, and I
Why
mean,
is that obvious?
you can observe. I mean, there's who your mother is, your aunt is, and so you can see the shared family ancestry.
So do you think that family trees through like ancestry.com don't work?
Of course they work.
Okay, why?
Because you're tracking the genetic similarities. So
exactly. So
right.
genetic similarity necessitates within species, it is necessarily linked to two things being more closely related to one another, right? So what I'm saying is, if it works within species, but it doesn't work between species, you have to pick where that line is drawn and be consistent with it. So if humans and chimps are genetically more similar to one another than either is to a gorilla, then there is no way to group chimpanzees with gorillas without grouping humans with gorillas too.
But the difference in your example is that the human ancestry, we already know about the human history. Okay, but
How?
For your grouping, okay.
How?
Well, I already gave the example. I mean, your family history. You can observe your family history. We can look at the genetics and we can see that they're like probably one mutation off or something from each other.
Well, we don't have the genetic history or I should say, we don't have the written down history of tons of people groups all across the planet. But we can do a family tree on them because, as you said, we can do the genetics. So what I'm saying is that, and we can do the same with dog breeds, and we can do the same with dogs versus wolves, and with the two of them versus foxes, and so on and so forth. So what I'm saying is that for a creationist to argue that this doesn't work, you're basically arguing that the entirety of Mendelian inheritance only works but up to a point, but you can't say where it stops working. So,
well,
unless you
actually,
have the answer, I've not heard it.
Well, and the difference though, and I didn't get to share this difference, is that for your grouping, you have to assume common ancestry. So, and that is a huge assumption. So it actually makes the whole thing circular, because you are starting with the assumption that apes have a common ancestor. Right? I'm not starting with that assumption. So just showing me similarities between apes does not show me that they have a common ancestor.
But that's not how comparative genomics works. That's not true, right? So the way that comparative genomics works is you sequence the whole genome of a critter, any critter you want. A human, a dog, a cat, a rabbit, a chimp, a baboon, whatever. Sequence their genome, line them up. Who's most similar to who? That's how you create the family tree. Now, that works exactly the same. I'm not kidding. It works exactly the same for Ancestry.com or for 23andMe. Any type of human phylogeny, the 1,000 Genomes Project did this. They took a bunch of humans, sequenced their genomes, And they grouped them together by how similar they were, because that's how it works with individual people. That's how it works with people groups. That's how it works with individual dogs and dog breeds. And that's how it works with species too. So what I'm saying is that by the exact same methods, by the exact same logic, humans and chimps end up being more similar than either is to a gorilla. So from a creationist perspective, either all 4 apes are not related at all, or humans and chimps are.
Okay, well, I haven't done the comparisons on other apes, but what would be the problem if all apes are genetically, they're not from a common ancestor?
What would be the problem, like, for creationism?
Right. I'm saying, how would this be? So I'm not proposing a specific model of creation.
Sure.
Yeah, I'm saying just separate ancestry.
So the problem for creationism comes down the line in a couple of different ways. So first, it comes from the fact that God has to create at the genus level, right? Because again, you're being consistent across all life, we should have a standardization process in science. So if you're being consistent across all life, we're talking about God not creating every species, but creating every genus, which is the level right above species. Because humans, chimps, gorillas, and orangutans, all 4 have different genera. Their genuses, for lack of a better term, are different, but they belong to the same family. So what that means is that every genus of critter would have to be a separate creation. And if that sounds like it works, you have to keep in mind that a lot of animals like lions, or like lions and domestic house cats, or like different species of hoofed animal, like antelopes, or like different species of bird that to an untrained eye, they look like the same animal, are actually completely different creations, which is possible, but not very intuitive. The much larger problem for creation comes with the ark, because we have the dimensions for the ark. We know how big the ark was, and we know for a fact you can't fit 2 of every species on the ark. Everybody agrees with that. Answers in Genesis, ICR, creation.com, creationists of old, all the way back to William Jennings Bryan and George McCready Price. It's too many animals, which is why they proposed the concept of created kinds, because then you don't have to take 2 of every species, you take 2 of every kind. The problem is there's almost as many genera as there are species. So if God creates at the genus level, that's too many animals for the ark. Now, there could be a supernatural explanation, but that's the basic problem.
Well, what's interesting is that this is getting into God, which we're just trying to figure out what is the positive evidence for evolution. And you're saying this, it couldn't have been this way because these, 4 apes, right? They couldn't be separately created.
But you asked. Yeah, that's what you asked.
Yeah. Okay. But then we can get back to the how is this positive evidence for evolution? And you're saying it works the same way from if you're doing ancestry.com with humans.
Yes.
And you can go all the way back to, fruit flies or whatever. And you didn't say fruit flies, but you're saying we can trace it, right? And what I'm saying is you can only do that if you assume common ancestry. If you're starting with common, and that's what I would like to see. So what is it? Yeah, that's making you
fair question, right? So all we do to come up with these family trees, right, for comparative genomics and for the sake of simplicity, is look at how similar 2 things are. How many base pairs do they share, right? There's no assumption of common ancestry there. You're just saying, how similar are they? How do they fit into, like, I would say a family tree, but you could do the same thing with like things that don't reproduce. Like, who's most similar to who? And then who's most similar out of the rest of them to those 2? And then once we have the 3 of them, who's most similar then? That's how comparative genomics works. Now, the reason it works that way in humans, for example, is because we watch, as you said, with our eyeballs, we watch humans reproduce. It's risque, but you can watch the whole thing happen. You do the same with fruit flies, you do the same with mice, whatever. You can watch them mate, develop a kid, have a kid, and you can test the genome of everybody involved. Without exception that I am aware of, 2 individuals that are related, like a parent and a daughter, are going to share more genetically than either of them does with a stranger. You know what I mean?
Absolutely. No disagreement there.
Exactly. Which means that their genomes are going to share more than either of their genomes do with the stranger if you were to compare them via comparative genomics. You can do this with populations of people too. You can take someone from Papua New Guinea and Scandinavia and from, Brazil or whatever, test them, and you're going to get a family tree of those individuals just on the basis of how similar they are. You're not assuming common ancestry.
No argument there.
Yeah,
We're totally on the same page there.
Right.
No argument. Okay. But you're extrapolating that to go further with other animals. So tell me how that works without the assumption of common ancestry.
I'm not saying common ancestry is factual when we do these comparative genomics. I'm saying that following basic observational empirical science, that is where this leads. Because we don't assume common ancestry when we test human genomes. There's no button that says, okay, assume common ancestry here. You're just sequencing the genomes and comparing them and then placing them, right? When you make that family tree, the family tree isn't saying these are all there's a common ancestor between all of them. It's saying who's most similar to who and then drawing lines to show who's most similar to who. Right? So you can do that at the population level. Again, you're not assuming that all these populations are related. They are, but you're not assuming that. You're saying, how similar are these genomes? Check. When you do that at the species level, you end up with humans and chimps sharing more genomically than either does with a gorilla. I'm not saying that proves common ancestry. What I'm saying is that is a massive, massive point in favor of what we would expect, and indeed what we did expect under evolutionary theory that was explicitly not proposed under any other model, creationist or otherwise, right? Everybody accepted probably that humans were going to nest as hominoids, like that humans would share more with gorillas and with chimps and with orangutans than they did with a random monkey. And that was true too. The surprise wasn't that humans nested with the apes. The problem was how closely they nested with the apes. Right? Because the way it was supposed to be was that humans are apes, but barely. And then it ended up being humans are more similar to chimps, and also chimps are more similar to humans than either is to a gorilla, which was a surprise because we thought that humans were the unique ones amongst the apes. And in some ways we are, right? In some ways we are, but in other ways we aren't. And it turns out that in basic genetic similarity, like base pair by base pair, that's how it hashes out. So humans, the way that this is support for evolution is that we are apes. The way that it's seriously in support of evolution is that we're a part of a dyad with chimps. Like we're the sister group to chimps, not the cousin. You see what I mean? Like that's where the support comes from. Now, to take issue with that, to say that that's assuming common ancestry, it isn't. Again, all we're doing is saying whose genomes are most similar to who. If common ancestry is true, humans must be apes if humans descended, I should say, not common ancestry. If our common ancestry with apes is true, humans must nest within apes. The fact that we nest with chimpanzees as a sister pair it makes it a guarantee. Because if that means if humans aren't apes, neither are chimps. You see what I'm saying?
I do, but this is the issue is that again, you can group things however you want and label them. So if you're labeling humans as apes because of the similarities that we share, okay, that's fine. But that does not at all, and you're saying the similarities that we have with chimps, right? It's unexpected. We would, by just the visuals, right? We would expect that they would group more with the other apes and that we would be farther. Okay. That's what you're saying. And you're saying that somehow supplies evidence that we came from a common ancestor. And I'm saying, I still don't see how that is evidence that we came from a common ancestor. Just sharing similarities, right?
Yeah.
Is not evidence of common ancestry.
So think of it like this. It's required for common ancestry, right? It has to be true. For common ancestry with other apes to be true, we have to group with the other apes genetically and physically as compared to monkeys. That has to be the case, right? Now, the way that science works is when we have a model and we make a prediction about something, if humans descend from apes, we should expect to see them share more with apes. If that turns out to be true, scientifically, and I'm just telling you as a scientist, this is how hypothesis testing and this is how it works. That is definitionally a point of evidence in favor of that idea. Now, if other ideas can also explain it, it's not. But if other ideas can't explain it, it is until you can find another way to explain it, which is why, and I think it was reasonable, you brought up, okay, well, what does this mean for creationism? That's why I said it creates a lot of issues for it, because at present, there is no model that exists that can explain why humans and chimps share more with one another by the same method that we create family trees in humans and with human populations. It groups humans with chimps and vice versa. No matter which method you use, using the most recent 2025 U et al. Paper, we get the same thing, every single base pair sequenced, right? So if you want to say that that's not convincing, that's fine. But if you want to say that that's not evidence in favor of evolution, that's definitionally wrong, because it aligns with the model that was set out and the predictions that were set out beforehand. And currently, no other model can scientifically explain it.
Well, and this is the thing, is that I will say that is parsimonious with your model, right? So
Yes.
it's parsimonious. The fact that humans, you looked at them, grouped them, and said, okay, we would expect this if they had a common ancestor. Okay, that's parsimonious with your model. And if you're saying, if we didn't find that, and it turned out to be something was the opposite, then that would be falsification of the model. Then, I would say that adds even more credence, right? But the issue that I'm taking with this being evidence for common ancestry is you're saying there's no other model, right? But
No other scientific model.
okay, so but all essentially that you're doing, and so it's not surprising at all, okay, that we see organisms that are similar, we group them together, and we've been doing this for a couple thousand years, right? Like we people have always been able to recognize morphological characteristics in animals and group them into various groups, right? So that the fact that we are similar to chimps, right? That's something you can look at and already group us together with the apes. As far as if we're going to compare us,
Right.
as you said earlier, to any other thing, we're going to be more looking like an ape than a starfish,
Sure.
right? So that doesn't actually supply positive evidence for common ancestry. It's parsimonious, but it's not evidence for.
So the thing is that that is what parsimony is, right? Like when we're talking about scientific models, again, I'm just using the definitions that I use in my professional life. Because this is parsimonious with human evolution, and as far as we can tell, again, from a scientific perspective, only human evolution, then it is evidence for human evolution. Unless you have a different scientific model that can explain it, it's not that it's parsimonious, it's the only explanation for now. Now, if you want to say, okay, well, it's common design, then my next question becomes, and I know this isn't the subject of tonight's talk, so we don't have to put it there.
Right.
My next conversation is, that's not scientific. There's no empirical means to define design. There's no empirical means to categorize it. Creationists don't have a way to tell the difference. And this is my biggest bugaboo with common design. They can't tell the difference between what's design and what's descent. Not genetically and not morphologically. There's no way to do it. And if the answer to that then becomes, well, it can't be done, then you don't have a scientific model. And it still remains the case that human evolution is the best explanation for the similarity between humans and chimps, to the exclusion of gorillas. Now we could have the conversation about the minutia. We could talk about U et al. We could talk about the Y chromosome that Donnie loves to talk about. We could talk about mitochondrial DNA or whatever. But we're talking about the biggest portion of the genome, the autosomes, and this remains the case. In fact, it remains the case if you look at what the letters actually do, the genes, across the board. But if you want, we can shelve that and go back to the fossils. Is that okay?
Yeah. We can go back to the fossils. I just want to make one final point on that.
It's your show.
That is, if you're saying this is evidence for common ancestry, right? There seems like there would have to be something to compare that to. So what I mean is so if I say that there's an intelligent designer, Okay. I don't necessarily have to propose, all the details of how that designer created, right? But it's still like I am proposing a different explanation that is just as parsimonious with the similarities that we see between
I
chimps and humans.
I think so. I have an issue with that because, as I said, as it stands right now, it's not scientific. There's no empirical means to get into that, which is why I was clear when I was saying that it's the best explanation scientifically. Now, if you want to include other ideas, that's another story. But here's actually a great way to dig into this a little bit more, and I encourage you to do this because I know you'll dig into this and hopefully talk about it another time. Run some comparisons or look up some comparisons of the similarity between humans and chimps, or humans, chimps, and gorillas, or humans, chimps, gorillas, and orangutans, however you want to do it, and a pair of organisms that you, Rebecca, accept as related. Like, I would guess that you would say that rats and mice are related. I don't know that you think that, but I would guess that you would accept that they're related. I would guess that you would accept that dogs and maned wolves are related. I would guess that you would expect that lions and tigers are related by common ancestry. That would be my expectation. All three of the pairs that I just mentioned are less similar in sequence identity genetically than humans and chimps are. Same with African and Asian elephants. I could go on, right? Because I've done this topic to death over on my channel. So what that means is that if this creates, as I imagine, a quandary for a scientific creationist, which is that you start becoming inconsistent. Because if genetic similarity can tell you that rats and mice are related and they're less similar than humans and chimps, then either they're not related or humans and chimps are. See what I mean?
Right. But I haven't proposed, that lions and tigers have a common ancestor. I don't know.
Right.
And I don't know about rats and mice. I would, if you grouped some organisms and said, pick one, you're forced to pick one that, have a common ancestor, then I would pick those. But,
sure.
But what I'm saying is it doesn't, cause a problem scientifically to just, observe animals, group them together morphologically, and, not have to say whether or not they share a common ancestor.
I agree with you at the basic level, but the second you want to start turning this into a scientific discussion, it becomes a real problem for creationism. Again, if you want to keep creationism as a non-scientific idea and say like God can tinker, God can do common design, but leave no, like in a way that isn't detectable scientifically, then I can't argue with you. Like if you want to say God could literally do it in any way and everything's on the table, like it can look exactly like evolution, but isn't, there's no argument to be had. Because at that point, and my opinion as, somebody who was a Christian at one point, my opinion is that violates Romans 1:20. But then again, many people have different theological opinions, right? Like I don't think God would be deceptive like that, but I digress. Fossils?
Yeah, well, and see, this is where we're getting into talking about religious ideas. And I think there is, as Cornelius Hunter said on my channel a few weeks ago, there are inherently religious ideas involved with evolution that are not recognized. And so my main objection is that you're proposing that what you're saying, this is all scientific, and that my story is not scientific. Now, I agree. I believe in a story, right? But my story isn't, I'm not going around telling people my story is scientific fact. And that is what you are doing. So that's why I don't want to get into various creation models. I want to talk about, because I don't know how God did it. I don't know how God did it. I don't know why God did it, except for the details that he's given me in Revelation. I mean,
I think that and I'm with you. I'm here to talk about the fossils. That's what I want to talk about. The reason why it keeps coming up, though, even though we're both trying to not talk about it, is because these things are intrinsically linked. Because the proposal of evolution is that it is the best explanation for modern biodiversity, including humans, right? The best implies that there are other explanations. And insofar as we can make sense of the data, it is the best. Does that mean that we will never discover something that changes our understanding of how biodiversity came about? No, science is provisional. That's its best quality, in my opinion, is the fact that it can change when new information comes to light. That's why it continues to work, no matter where and when it's used. But this keeps coming up necessarily because the implicit sort of assumption, or not assumption, the implicit underscore of this show is that evolution doesn't work, something else does. So as somebody who's proposing this is evidence for evolution, you say, well, that could be explained by other things. I do think that I'm within my right, and I think it's a fun thing to discuss, to say, okay, well, what does then? You know what I mean? Like, I'm with you, though. I want to keep it on positive evidence for evolution.
Yeah. Okay. And I definitely understand your complaint, but I will have to push back on this idea that right now evolution is our best explanation. So what are you comparing evolution to say it's the best explanation?
Anything and everything else. I've never, in my field, which is arguably the most personal with regard to the theory of evolution, human evolution, nothing even comes close. Right? I mean, I've worked at these sites. I've put my hands on these fossils. I've measured them with my own calipers. I've scanned them. I've been all over the world and seen them, and nothing else comes close. Right? Like, and I've seen everybody's perspective. I've seen Peter Lyne's. I've seen Carl Werner's. I've seen Donnie Badinsky's. I've seen not Biologos, Todd Wood at New Creation and Peters. I've seen a ton of different perspectives. None of them explain it. And that's what I hope to get into today, because what was predicted for evolution, which is that we should have the slow emergence of human characteristics and just an entire menagerie of mosaics, transitional forms, we have that in human evolution in spades. And I think that's especially important for creationism, because somebody can sit around all day and say, well, we don't have all of the transitional species for bats, or we don't have all the transitional species for eels, or we don't have all of the transitional species for anglerfish, and thus creationism might have a dog in the fight. The problem is, if humans evolved from more basal apes, creationism is dead in the water. Theistic evolution isn't. That's fine. Like, you can still be a Christian and accept evolution, absolutely. But creationism in its old and young form are toast if humans evolved from other apes. And that's why I think that this line of evidence and this particular lineage of transitional fossils is so problematic.
Okay. And so, but like you're saying that there's basically all the comparisons you made are all creationists, right? So is there any other possible model? Because why is this the one model? Like, is there another scientific model that you could compare it to?
I don't think that, well, yes. I mean, for most of the history of science, there was species fixity, which was the idea that species didn't change all that much, or they could change a little bit, but only within their groups. And this wasn't intrinsically, well, I shouldn't say that. It was intrinsically tied to God, because these were gentlemen naturalists who were proposing it in the UK and in Europe 200 plus years ago. So it was intrinsically linked to God. In fact, most of science was during that time. Evolution was as well. Darwin was a Christian when he proposed the theory of evolution. He did not lose his faith until later in life. So to many people, this wasn't an issue. But yeah, I mean, I ask, like, is there a way to have, like, do you know of another model that tries to explain it? Because I've seen just about every idea trying to explain evolution or trying to explain hominins in the book. And if it's not the regular conventionally scientific one, it's usually coming from a religious perspective.
Right. And actually, that kind of gets to the heart of what I think evolution is. It is a religious perspective. And so that's why I want to harp and like show people that the scientific evidence is actually against evolution. It's actually religious at heart.
Well,
And so that's illustrated in that a lot of your arguments, you even said, I don't know why God would do it that way. And so a lot of the arguments are really, when you get down to it, the foundational thing is that, this had to happen by natural processes.
When I said God wouldn't have done it that way, I didn't mean God wouldn't have done evolution that way. I meant God wouldn't have done non-evolution in a way to look like evolution. Do you see what I'm saying? It wouldn't be intelligent design, but look like evolution if God is an honest is honest in his representation within his own creation, right? I'm not saying God wouldn't have done it via evolution. For most of my life, well, maybe not most of my life, but for a solid chunk of my life, I was a theistic evolutionist. Not only do I think they have the best case scientifically, I think they have the best case theologically, personally. I don't even think young earth creationists have a leg to stand on, scripturally speaking, and certainly not, and I'm almost an expert on this right now, not historically, right? I mean, young earth creationism is very new, historically speaking. This comes about mostly in the 1920s. There were some stragglers prior to that, but that's a story for another time. I'd love to discuss it with you, but
yeah, we can do it another time, because I want you to be able to get to your fossils.
Yeah.
Before, you gotta go.
Can we agree beforehand that the expectation, the prediction by evolution is that if humans evolve from more basal apes, we should see that happen across the fossil record. We should see oodles of transitional forms with a mixture of not just ape and human characteristics, but we should see a bunch of fossils whose bones themselves are a mixture of ape and human characteristics.
So you're asking me to say what your theory should do?
I'm saying if evolution made that prediction and that's what we find, is that evidence for evolution in your eyes?
I would say that it's certainly not evidence against evolution, but I would say you would need more than that.
But what we're doing here, like what you said at the top was with Grayson, you were like, Tiktaalik, Archaeopteryx. These are evidence for evolution, not evidence evolution happened, but evidence in favor of evolution because it was a prediction, then it was discovered. If I show you the same thing with hominins, is that going to count for you by your standards?
That's going to count.
For evolution? Okay.
That's going to count. But I do want to make clear what I'm crediting Grayson with, and it'll be the same thing that I'm crediting you with if it's true, right? And that is the prediction of what is expected, right?
Yes.
So for me, I don't see Tiktaalik as a transitional form, but I'm willing to grant that that was a prediction. And actually, not just Tiktaalik, but also Archaeopteryx have now been shown that they're not really in the lineage that we would expect, according to the phylogenetic trees. So they don't really fit into a nice space of being a transitional form. But what I granted him the prediction about was that, that they predicted that we would find such a creature that might have some of those transitional forms. And so I'm happy to do that with the hominin fossils as well. Okay.
That's all I ask.
Okay.
All right. So we're going to talk about humans and their physical evidence between these other hominins. So in order to talk about how we see the emergence of these characteristics through time, we have to say what those characteristics are. So what you can see on your screen here is over on the left, these are some Miocene apes. These guys, if you saw them today, you wouldn't look at them and say they're anything other than some kind of ape, right? They're tailless, monkey-looking guys. They hang around in the trees. They eat fruit. They got big canine teeth, etc. Whereas currently we have humans, and humans walk upright, and we have a bunch of different interesting characteristics within it. So we need to basically go from this type of form here to this type of form here. So the characteristics that define a human to the exclusion of other apes are these. Humans walk upright all the time, right? Chimps don't walk upright. Orangutans don't walk upright. Gorillas don't walk upright. They can, but they don't tend to do it, right? And in accordance with that, we have a lot of physical skeletal characteristics that necessitate us walking upright. Our pelvis has this bowl shape to it. Our knees come in at an angle. We have a toe that's in line with the rest of our toes to help push off instead of to the side to grip branches. The hole at the base of our skull, the foramen magnum, is tucked up underneath the skull so that our head can sit on top of our vertebral column, and we can survey the landscape. There's a lot of characteristics that make you a biped instead of a quadruped. Biped just means walking on 2 feet. That's something that only humans do amongst living apes. We also have really big brains. We have little canine teeth that don't keep themselves sharp. So there's something called the canine P3 honin complex that keeps the canine sharp. We don't have that. All other living apes do. We have a broad dietary niche, and we use a lot of different types of tools, and we take a long time to grow up, right? Now, other apes take a long time to grow up too. An orangutan baby will stay with its mom for upwards of 8 years. The max is like 12 years. Humans stay till we're 18, sometimes even more. And that shows up in our physiology too. So here's a little image to show you how humans have really big brains and how our brains differ from those of other apes. And here's a comparison of a chimpanzee skull here on the left, or chimpanzee skeleton here on the left and a human skeleton here on the right. In a lot of ways, they're really different. I hope you can see that the most striking differences come in the form of the pelvis or the hip bones, the feet with the toe, the long arms relative to the legs in the case of the chimpanzee as compared to the human, and so on and so forth. Canines, here's a picture so you can see, right? Chimpanzees have big canines, humans have little canines. And in chimpanzees, or rather in gorillas, the males and females tend to have differently sized canines, so they're dimorphic. That's not the case in humans, and it's not the case in gibbons. We eat a lot of food, we use a lot of tools, so do chimps, but humans take this to the next level. And extended time to maturity, this is to just show you what I mean here. In chimps, they're born, they have their infancy, they have their juvenile period, which is after their first molar has erupted, and they get weaned at the same time. And then they hit physical and sexual maturity at the same time. So they're finished growing and they are ready to reproduce at the same time. This is way more spread out in humans. And this records itself in our bodies. It records ourselves in our teeth and how they erupt, in our growth plates. You can actually tell the relative age of an individual of any skeleton just by looking at its growth plates and at its teeth. So hominin species should display the emergence of all of those characteristics through geologic time. So let's start taking a look. I don't think this is controversial to say, but I'm going to say it anyways. If you find all the characteristics that humans have that make us walk upright all the time in a fossil, it walked upright all the time, at least when it was on the ground, right? You're not going to find a human-like pelvis, an inline big toe, 3 arches in the foot, an anterior foramen magnum, an S-shaped spine, like all the characteristics that allow us to walk upright. If that's in a fossil animal, it doesn't just mean that it could walk upright, it means it did, right? But probably still spent some time in the trees too, some of the time, but if you find those characteristics, it was an upright walker. And the reason I say this isn't controversial to say, hopefully, is because if your foramen magnum or the hole at the base of your skull is in the back, more like a chimp as compared to a human, which is more in the front, if you try to walk like upright, you're going to be staring up. And if you're a human and you try to walk quadrupedally, you're staring directly downward. It's just not feasible. All right, so let's talk fossils. I have these like brain case size overlaps here just so you can see that we're going to watch brain case size increase over time and that all of these guys are going to overlap with one another. Now, again, keep in mind, this is the prediction that was set forth by evolutionary theory. It is most parsimonious with evolutionary theory. Nothing else, in my opinion, can explain it, as hopefully I will demonstrate here in a moment, which means it's evidence for evolution. The oldest fossils that we have are from these hominins called Sahelanthropus chidensis and Ardipithecus ramidus. They're not very impressive. Their brain case sizes are actually pretty little. You can see them here across geologic time on the x-axis and brain size here on the y. Modern human here, chimpanzee here, and then here's a Miocene ape, and then here's Sahelanthropus and Ardi. Through geologic time, they're really nothing impressive. Here's Australopithecus. So you already see it's a step in the human direction. There's Paranthropus, another hominin set of species. And then here's all of genus Homo, all of genus Homo. Now, what you'll notice, hopefully, and I'll click here so you can see it together, is that Australopithecus, which is in green, overlaps with Paranthropus. Australopithecus and Paranthropus overlap with early members of genus Homo. Early members of genus Homo overlap with later members of genus Homo. Later members of genus Homo overlap with even later genus Homo, including humans, Neanderthals, Denisovans, etc. Right? These are not discrete. These bleed into one another. The highest Australopithecus brain overlaps with the lowest Homo erectus brain, which is important because this shows us that these aren't groupable into discrete categories. And it is precisely what one would expect and indeed predicted if these animals are growing their brain case size over time. This holds for their EQ or encephalization quotient, which just means it holds if you take body size into account. So do we see large brains increase over time across the hominins from older, more primitive hominins to modern hominins? Yes, we do, right? That is exactly what we would predict from evolutionary theory. Maybe you can explain it again by other hypotheses that I've not heard of, but necessarily evolution predicts this, and that's what we find. So, do we find bipedalism emerge? Now, this is something that I think is important to talk about because bipedalism involves a ton of different characteristics all changing in tandem, more or less. Now, the fossils that you can see on your screen now over here on the right, this is Homo erectus. I don't think anybody's going to look at this guy and say that guy right there is not a human. At the same time, this is Lucy's species here in the center. Now, Lucy's species is inarguably bipedal. There is absolutely no way to argue against this to the degree that I've seen a lot of creationists come around to just accepting that Lucy's species was some kind of random upright ape. But yes, she's got this bowl-shaped pelvis. She has arms and leg ratios that are closer to humans than they are to chimpanzees. She had an inline big toe. I'm saying her genus, not this individual specimen here. She had an anterior foramen magnum. And so if we look at Lucy and we say that thing's already bipedal, then the emergence of bipedalism had to come before Lucy. So we should have a transitional species, not just as the bipedal Australopithecus. And I think a creationist would agree with this. If Lucy's species is already bipedal, you have to show the transition to that bipedal species. And that's what we see in this hominin that existed a couple of 100,000 years prior to Lucy, this animal called Archaeopteryx ramidus. So Archaeopteryx ramidus.
Wait, can I stop you right there? Because I have a question about Lucy. Can you go back to Lucy? Okay.
Of course.
And this is not a question challenging your evidence. Okay. This is a question to help me get your expertise regarding a creationist argument right now. Okay. Yeah. So do you think Lucy was an obligate biped?
She was an obligate biped when she was on the ground. Yes. But she still spent some time in the trees.
And I would like to separate the rest of Australopithecus afarensis from the Lucy skeleton in particular. So there's an argument that some creationists are making saying that Lucy didn't have like weight-bearing capability in the same way that humans do. Okay. And the reason this is important is because there's another creationist that's saying the Lucy skeleton is actually human.
Yeah, there's no way. And actually I had this conversation with Donnie when I gave this same PowerPoint presentation to Jerry Bergman. I had this conversation with Donnie. Lucy's not a human. And the reason we know this for a fact is because the elements that you see preserved on Lucy right now, we have in like probably 4 or 5 other, more in some places, complete skeletons, and then a few about as complete, and then a few less complete skeletons. And in one case, actually in 2 separate cases, the skeleton that we're talking about that's also a member of Australopithecus has full articulation of some of these bones, which means the bones are preserved still touching one another as they would be in life. And we have Australopithecus remains connected to the pelvis. Like everybody agrees that these are Australopithecus remains that are connected to the pelvis, which means that pelvis can't belong to a human unless a human and an Australopithecus slammed into one another, like going at top speed and accidentally, like just to make it look like their bones were touching, right?
Yeah.
Like for example, Australopithecus sediba, the pelvis of that animal looks identical to Lucy. Like they're very, very similar. To a layman, you wouldn't be able to tell the difference. But the lumbar vertebrae that's connected to that pelvis is like undeniably an Australopith vertebrae, but it's connected to a pelvis that somebody who would say that Lucy is just a human pelvis, that it looks exactly the same.
Okay, so is the articulated one you're talking about Littlefoot?
No, Littlefoot is another example, but I was talking about MH2.
Okay, I was just curious. Okay, but do you think that at this point, so Lucy was an obligate biped?
Lucy was an obligate biped when she was on the ground. She still spent some time in the trees. But when she came to the ground, this animal could not, no member of Australopithecus could walk in any way that wasn't upright when they came to the ground consistently. They would be an obligate biped in the same way that a chimp isn't, for example. Like,
so is there any difference between the way that humans' pelvises are shaped and Lucy's?
Yeah, there are slight differences. I mean, you can see that if you look at the screen now, you can see that there are differences between that Australopithecus pelvis and Homo erectus there on the right. But there are also differences between that Homo erectus on the right and a modern human pelvis that are as extreme as the differences between Lucy and that Homo erectus pelvis. So what I'm trying to say is that for the ways that pelves differ, the variation is significantly lower when you're a biped, because the shape of the pelvis has to be in that bowl shape with the ilia or the blades of the hip running front to back. And the reason is because they anchor your glutes. Like biomechanically, you have to have really powerful glutes to stay upright. That's why chimps and gorillas can walk upright, but they're really, really bad at it. And they can't fully extend their knee in an efficient way that is going to allow them to move upright all the time.
Okay. So like you would say like Lucy's hip is the same type of, and again, this is like for an internal creationist argument. Okay.
Yeah, sure.
But just you would say that it's the same weight bearing as a human pelvis, like generally speaking.
The purpose of the pelvis isn't like it's not really weight. It's not, the purpose isn't that it's bearing weight. Usually that's like a knee thing, right? The weight bearing of the knee tends to be valgus, so it comes in, as you can see on Lucy and on Homo erectus there. But yes, in all biomechanically relevant ways to walking upright, Lucy had every characteristic required to walk upright, and in fact, those same characteristics restricted her from walking in any other way.
Okay, awesome. Thank you so much, because I love getting an outside perspective, and you have no skin in the game on this particular argument, so I consider you a good, source for this information.
Here's a perfect one to talk to people about this, Rebecca. If people are giving you grief for this, there's a structure at the anterior front portion of the human pelvis called the anterior inferior iliac spine, the AIIS. This is a structure that is critical for bipedalism. When it's underdeveloped in people, it can lead to serious pathologies in walking, right? So like it's necessary. It's this little ridge that you can see on the front. It's only in humans. It's not in chimps. It's not in gorillas. It's not in orangutans. It is in Lucy. It is in every Australopith that we have. They have that same anterior inferior iliac spine, and it's obvious. Like it's this big ridge of bone that you can see in the front. That's critical for bipedal walking, and her and all of her relatives have it.
Okay, awesome. Thank you. And nobody's giving me grief. I'm just trying to figure out who to believe. So, okay, you can keep going with the next one.
Yeah. So, but this is the thing, right? Like if we agree Lucy's bipedal, then evolution has to provide for us a transitional species to that biped, right? Like we need to see something that's in between a Miocene ape that wasn't a biped and Lucy that is. And that's what I'm going to show you next. The pelvis of the animal that you can see now is from Ardipithecus ramidus. So it's here in the black running up and down, and then it's pivoted again in the blue. And over here on the right are like where you can see my cursor with these little cartoons at the top is a human pelvis viewed from the side compared to Lucy's pelvis viewed from the side, or I should say Lucy's species pelvis viewed from the side, compared to the fossil we're looking at right now, Ardipithecus ramidus, compared to a chimpanzee, right? Now, what's interesting about this is if you look at the bottom, chimps have really tall pelvises and humans have really short, squat pelvises. Again, we're anchoring those glutes on the side. And I don't know if you can see my cursor, but this ridge that I'm indicating right here, that's your anterior inferior iliac spine. Okay. You see how like massive and jutting it is? And chimps don't have it. This is actually the top of their ischium, I think. So it's a totally unique structure to humans. Humans have a short ilium, that's the blade, and a short ischium, that's this bottom part. Chimps have tall on both. But this fossil that we're looking at here, Ardipithecus ramidus, has a short ilium like a human and a tall ischium like a chimp, and it has an anterior inferior iliac spine like a human or like Lucy would, right? I mean, this thing is unique, and yet its brain is this one right here in blue. Tiny brain. Another total pinhead that's walking upright like a human when it came to the ground. Now, no doubt this thing came to the ground less often than Lucy's species did, because its pelvis is like halfway in between being a biped and being something that, like being a committed biped on the ground and being something that mostly spends its time in the trees. So like we can make a prediction here, right? As the authors did, what kind of environment would an animal with a pelvis like this live in, right? If it has part of its pelvis that's chimp-like and it's all in one piece, as you can see, if part of its pelvis is chimp-like and part of its pelvis is human-like, where would it live? And the answer is it lives in an environment that's characterized by clumps of forested trees and separated out. These groves of trees are separated out by swaths of grassland. So this is an animal that spent time in the trees but had to come down to move from tree patch to tree patch so that it could forage, right? We see something similar in modern day gibbons, who will only come to the ground when they absolutely have to. But this animal's environment was changing, so it had to come down far more than a gibbon ever would, and its anatomy started to change to reflect that. In the paper that I just showed you, you can actually see that these are all of the measurements of Ardipithecus ramidus's pelvis compared to a gorilla, a chimpanzee, Lucy, and humans. And you can see that in some ways, in most ways, 3 out of 4 here, it looks like a human, but in some ways it still looks way more like a chimp. But this is one bone. This isn't just like a transitional species. This is a transitional bone inside a transitional species. Here's the comparison here to show you that it's got that anterior inferior iliac spine. And then here's a comparison of some of the long bones here. Now, what this tells us, in addition to the fact that Ardipithecus ramidus had an anterior foramen magnum, its head was on top of its spine, and I have the model back here if you want me to get it out to show you, but that hole at the base of the skull is way more forward than it is in a chimp. So this thing has a more human-like pelvis and a more human-like positioning of the skull, but it still has really long arms, and hopefully you can see here at the bottom, its big toe sticks out to the side, like a chimp's does. But this is an animal that's spending a lot more time on the ground than any of the Miocene apes that came before, and we know that because that's what its environment necessitates. Hopefully you can ignore my dogs here. So this acts as a major transitional species in numerous different bones. Again, as you can hopefully appreciate here, because the scientists took the time to measure it all out, between those Miocene apes that I showed you at the beginning and Lucy. So we've got transitional species inside a transitional species. I was talking to you about how Australopithecus is bipedal. Here's MH1 and MH2 here. That's the one that I was talking about. So you can hopefully see there's the pelvis and some of the vertebrae that are connected to one another. There's Littlefoot there. Here's another Australopithecus afarensis partial skeleton. Here's another preserved pelvis from Australopithecus africanus. This is also Australopithecus africanus here, full pelvis preserved and a spine that's still able to fit piece by piece together. This cervical spine down here, so the spine of the neck, was found coming out of the skull of this kid here, of Australopithecus afarensis. Here are a handful of skulls. I've seen some of these skulls. You can flip them over. They all have anterior foramen magnums. The hole at the base of the skull is forward in all of them. This is not, in my opinion, up for debate. And you can chart it, right? Like they've done these measurements. You can actually see where they fall and see like who's who. Here's that one that I was telling you about where there's the spine literally coming out of that base of the skull. And here's where it maps. Australopithecus is highlighted here by my cursor, and then non-human apes are way down here. It maps with Homo erectus. It's even higher than some members of Neanderthals. Pelvis, it's human-like. I don't think that's up for debate. You can see a couple of different pelvises from a couple of different specimens here. There's Lucy. Here's, I believe that's Africanus again. And this is MH1 and MH2, I think. I'm not positive. Again, seeing is believing. You don't have to be an anatomist to pick the odd man out here. I mean, the pelvis is that of a biped. And when I say it was that of a biped, I mean, you can't take this pelvis and make it belong to a quadruped. There is zero example of that in nature. They've done some really cool geometric morphometrics on this. So this is basically like they 3D scan a bunch of pelvises and then plot them to see how that entire shape maps with everything else. Here's humans in orange over here. Here's Australopithecus just below humans, really similar but not identical. And then there's Ardipithecus ramidus, that one who I just told you has that transitional pelvis, literally straddling the difference between living apes and humans. And that's because the top part of the pelvis is human-like and the bottom part of the pelvis is ape-like. Now, again, a creationist could look at that and say, well, maybe it was designed to live in that environment. God could have done it that way. Sure, he could have. I agree. He could have done it that way. But that doesn't change the fact that this is an explicit prediction made by evolution, that we should see these animals with mosaic bones in mosaic species living in mosaic environments leading from Miocene apes to humans. You can see it in their cortical bone too. Here's Lucy's femur, right? Over here on the farthest right is a CT scan. The cortical bone, or like hard non-spongy bone in humans, is harder and more it gets laid down thicker on the underside of the neck of the femur here. And that's because we walk upright. This is where a lot of that weight is born. In chimps, it's equal in the top and underneath, as you can hopefully see. And that's because chimps don't walk upright all the time. But in humans, not so. And then here is our Australopith over here with that cortical bone distribution unambiguously in this CT scan here, reflecting the human pattern, not the chimp pattern. Their knees look like ours. It's valgus and comes at an angle. You can see that in this figure up here or down here. Sorry, my dogs are going crazy. And you can see like scientists talk about it. Feet, same thing. Lucy's genus had an inline big toe. That's not avoidable. Again, the portion of the toe that articulates that metatarsal that articulates with the tarsal bones here is in line as it is in a human. Again, I want to emphasize, like, we've mapped this out. You can run these comparisons for yourself, but like, this is a prediction that evolution makes. Creation can try to accommodate it. God could have done it that way, but it maps precisely with what we would expect and said outright we would see if humans evolved from a non-bipedal ape. What's cool about the Laetoli footprints, a famous trackway that was proposed to be made by Australopithecus, is that I hear from creationists a lot that it's like, well, they only said that it was Australopithecus because it was in the wrong time frame. Those are really just human footprints, not Australopithecus footprints, and they're just forcing it to be Australopithecus. No, we've done the biomechanics work on this, so like taken scans and casts of these footprints, and the Laetoli footprints mostly map with humans, but you can see here in this graph that line is the average for each footprint, and humans map down here and chimps map up here. Where's the Laetoli footprints? It's in between, way more similar to humans than it is to chimps, but it's in between these two averages. Same with when you look at how the weight is actually born. They heel strike super hard, more like a chimpanzee, but then they have that inline big toe and 3 arches in the foot, like a human does. So they're walking upright just like us for sure, but they're not doing it in exactly the same way. Sorry, I'm gonna pause for a minute and yell at these guys.
Awesome. Thanks for being here, everybody. I appreciate all of you. Let's see. Hello to Dave. Hello to Wesley. Hey, BS. Hey, Antonio. Good to see you. Tom, Mabus. Nice to see you. Golden Alt. Don't remember seeing you before. Sophia, good to see you. Thanks for being here. Okay, go for it.
Yeah, sorry, I yelled at them and got mean. Now, Australopithecus absolutely still climbed. It had to. In fact, what would we expect from a transitional species that's moving from the trees to the ground? That one day it just immediately commits to the ground? That's not the expectation. Animals don't do that. Instead, they transition to that lifestyle, which means necessarily if humans evolved from a tree-dwelling ape, there was at some point an ape that was spending some of its time in the trees and some of its time on the ground, and then eventually most of its time on the ground and occasionally going into the trees, which is what we see with Australopithecus. It has features of its shoulder blade or scapula that look more like humans, and it has features that look more like living apes. So here you can see bonobos and chimps, gorillas, and then siamangs and gibbons. Humans are way over here on the right in this sort of lavender color. And then here's Australopithecus, again, right in between the two of them. And then you can look at the curvature of their phalanges. You can look at the curvature of their ulnae and radius and tumors and things of that nature as well. So Australopithecus was bipedal when it was on the ground. It still spent some time in the trees. It has all of the necessary characteristics, not just to be a biped, but those characteristics are human-y. They're specifically in the direction of Homo sapiens, not in the direction of a completely different hominin, which theoretically is possible. Like, I suppose you could evolve a totally unique pelvis, but instead they have the characteristics that denote human bipedalism, and then they have aspects of their bipedalism that is unique too. So those are your bipedal characteristics shown emerging slowly over time. And the reason I've stopped after Australopithecus here is because if Australopithecus is bipedal, then that's done, right? Like that's already arrived. Nobody at that point, you don't have to evolve anything new. Now, what I will say is that you see the honing of the bipedal characteristics in Australopithecus as you move to humans. Arms get shorter, legs get longer. The striding bipedalism unique to humans arrives. Bodies get bigger. The rib cage gets less bell-shaped like that and sort of slenders out. The spine has a more efficient curvature to it, and so on and so forth. But the overall basic bipedalism transitions from Miocene apes through Ardipithecus and into Australopithecus, and then it's done. Canines are the next thing. I love studying canines, or I love talking about canine teeth because that's what I study. Jeez Louise, because that's what I study fundamentally. And so hopefully you can see here, here's a chimpanzee canine, and then here's a human canine. This is Australopithecus afarensis. So Lucy already had small canines, just like humans, and she had small canines in both sexes. That has not happened in any other Miocene ape lineage that I've studied, at least not that I can show yet. It's unique to the hominins, which means that it arrived in Ardipithecus ramidus, was maintained through Australopithecus all the way to humans, or it happened 3 separate times, which is not very parsimonious at all. You can see it already occurs in this sort of flow chart that you can see here that plots, again, through our transitional apes all the way up to Australopithecus. By the time you reach Australopithecus, like I said, it's already small. But it's not just that the canine gets small, that honing mechanism also disappears. And so what's really cool is that this skeleton here that I was just telling you about, Ardipithecus ramidus, this thing has canines that are still like a little bit big. They're way smaller than Miocene apes, but they're still like decently sized. But what's fascinating about them is they don't have a honing complex. The honing complex has disappeared, even though the apes that immediately precede Ardipithecus ramidus, members of its own genus called Ardipithecus cadaba, who you can see, I believe, in one of these. Yeah, in this figure here, Ardipithecus cadaba is in dark pink. They have canines that are the same size as Ardipithecus ramidus, but they still hone them. So in about 500,000 years, in one single genus, we see the loss of the honing complex, and it never comes back. And those teeth stay small as well. That's awfully strange if these animals aren't related. And they're non-dimorphic as well. Tool use is really cool to talk about because Australopithecus used tools, and they cut bones too. So these are cut-marked bones from Tiktaalik, actually the same site that cervical spine coming out of the skull comes from. Here are the Lomekwian stone tools. These were made by Australopithecus or Kenyanthropus, depending on who you're talking to. Again, these were animals that were using tools. And so we can make another prediction here. If humans evolved from Australopithecus, if genus Homo evolved from Australopithecus, then the tools that they use should slowly start getting more advanced as we move through geologic time, right? Like the tools should evolve with the hominins if the brains are evolving, and that's what's letting them get bigger tools, and human evolution is true. Yes?
That sounds good to me. But my question is, are we finding these tools with those creatures?
Yes.
And how are we? Go ahead.
Oh, go ahead. You go ahead.
No, because this will take us on a different subject. I want you to finish what you're going to say. Go ahead.
I'm almost. This PowerPoint's almost done, and then we can sort of refer back to these as if we continue to talk about it. The way that they're associated with hominins, like this hominin was capable of using this tools, is by looking at absolutely every animal that was around at that site and seeing if anything else could have possibly used them there. So I can foresee the question you might have there, and we can talk about that when we get to it. After Australopithecus here, who's using the Lomekwian stone tools, the earliest members of Homo advanced their tools. So this is like 500,000 years later. The hominins have changed, and the tool types that they use have changed, and their brains have gotten bigger, but not by much. So you can look at these two stone tools and say, oh, Lomekwian, like those are kind of garbage, like they kind of suck compared to the older one stone tools, and you would be right. But what's crazy is if we go back to our brain case size chart, which is right here, early Homo and Australopithecus overlap. So the earliest members of genus Homo, of our genus, had brains that reached down as low as Australopithecus in size. And they used tools that were only slightly more advanced. So slightly bigger brain, slightly better tools. That sounds like slow gradual evolution to me. And that continues onward. After the Oldowan, we reach the Acheulean, better stone tools associated with Homo erectus, bigger brains. sort of like, again, exactly what you would expect. And the Acheulean eventually becomes the Mousterian for Neanderthals, and the Aurignacian when we talk about humans. One of the coolest recent bits of history that we've seen, or recent bits of paleoanthropology that we've seen, is by demonstrating the human-like growth pattern. And the reason this is cool is because we erupt teeth at like really predictable ways. So like that little bit that I showed you earlier, that's like a timeline to show you how things grow up. Humans and chimps are both born. We're both babies. We're both infants. Chimpanzees have their first kid molar erupt, right? And they're weaned from their mom, so they stop drinking milk at about the same time, at about age 4. Whereas humans get weaned way before our first teeth start to erupt. Then chimpanzees reach physical and sexual maturity. Sexual maturity is defined as first emission for males and first menstruation for females, but this is rarely the time at which they first actually have a child or engage in sexual activity in most societies. In chimps, physical and sexual maturity happens at the same time. So they're done growing, they don't have any more growth spurts or anything like that, and they reach sexual maturity, same time, done deal. Whereas in humans, first emission and first menstruation occur way earlier, right? Like way earlier, unfortunately, than when physical maturity ends. Like kids are still undergoing growth spurts when they're in high school, and yet they can become teen parents, which is unfortunate, but true. Now, these mark themselves, like I said, in the long bones, so in growth plates of the bones and in how the teeth erupt. And if you're female, in the front portion of the pelvis, you can tell if a woman has had a child or not, just from the pubic symphysis, where those two halves of the pelvis meet. So we can figure out where, like, how old a lot of fossils were when they actually died. And when we look at Homo erectus and some of our earlier hominins, we have this interesting conundrum, because Australopithecus had an ape-like growth pattern, like a chimp-like growth pattern. They grew up like chimps did, where they had 3 stages and they reached them in these neat little areas. Whereas later members of genus Homo, like Neanderthals and humans and Denisovans, they grew up like humans did. So we should expect then evolution would predict, and did predict, that we should have fossils that preserve this change as it happens. And we actually have that in beautiful spades, right? So in these guys here, these are earliest members of Homo erectus. I would call them Homo georgicus, but some people disagree. These are the Dmanisi hominins. And what you see here in figure 3, this is from a paper by Zollikoffer et al. In 2024, so a relatively recent paper. You can see that in red, we have our humans. So this is the age here on the Y, or on the x-axis, so how old they are. And this is their tooth eruption on the y-axis. So as you can hopefully see, chimpanzees have like this very particular pattern in how the age that they're at and when their teeth erupt, and their sexual and physical maturity occur at the same time, whereas in humans, they are decoupled. And these Homo erectus members, nobody would look at these guys and say they aren't human, have a more ape-like pattern. They didn't grow up like modern Homo sapiens. They grew up like chimps. Not exactly like chimps, but more like chimpanzees than humans. Which is to say, but what's cool is that it doesn't start that way. So this is like a neat little graph that shows slightly more in depth what I'm trying to say there, is that they start growing up slow and then they speed up to match the chimp rate in the case of these early members of genus Homo. And just a couple 100,000 years later, later members of Homo erectus, or what I would call Homo erectus sensu lato, are even closer to humans. So here's the human here highlighted by my cursor. Here's Australopithecus. Here's these specimens of Homo erectus, smack dab midway between humans. So whereas these guys would have been slightly closer to the Australopiths, Homo erectus, like, again, these were people who like used fire to cook their food and wore clothes and used advanced technologies and expanded out of Africa. They're growing up midway between humans and chimpanzees. For the record, this is not explicable by environmental conditions. Human hunter-gatherers do not grow up like chimpanzees do. They grow up like humans do, because they're humans.
Yeah, and just for people watching, my view is that Homo erectus is just a human. But
right.
The regarding how do you know when the teeth eruption happens? Like, are you comparing like ages? What do you? I mean, like, you know what I mean? Like,
yeah,
maturity,
so
ages and stuff like that. How many? Yeah.
So if a kid, unfortunately, like, and this is sad to think about, but like if a child at age 6 dies and then their skull preserves, like for instance, some of the kid australopiths that we were looking at earlier, they wouldn't have all their molars, right? The teeth would still be in the jaw, developing in what we call the crypt. So like theoretically, you could cut the fossil in half and you could see the teeth still sitting below the gum line. They haven't erupted yet. So what you can do is you can pull these fossils, right? And because life was a lot harder in prehistoric times than it is now, a lot of hominins died young, which means that you can get their age by when their teeth erupted and by when their growth plates closed, because those two things can be timed with each other. So like your growth plates are these plates that exist at the ends of your long bone. So like at the ends of your femur or at the ends of your tibia. And they facilitate the lengthening of those bones as you grow and as you age. And once those growth plates close, you're done growing. You've reached physical maturity. So you can use both of those two things to time the age of the individual.
Like yeah, and I'm just curious, like how many bones are we looking at to compare for Homo erectus? Like the ones that you're saying, we know that they were more similar to chimp.
Yeah.
How many like specimens are we looking at?
I'm not sure off the top of my head. If I had to guess, I would say like for all age ranges, a dozen or so would be my guess.
And the ones that we're seeing the teeth in that configuration that you're saying is more like a chimp is like 12.
Say that one more time.
I'm sorry. I'm saying like are you saying we have 12, like roughly 12 specimens that are showing the teeth that are more similar to how ape, or Australopithecus development goes with teeth?
Yeah, for charting the ages, that would be, again, that's my guess. We can check this at the end of this. We can check this paper and just see for ourselves, though.
Okay, cool.
Because this is the exact paper. I'm not sure how many individuals are at this site at Dmanisi. These are the 5 best preserved skulls or crania of the individuals, but obviously we have far more like partial jaws and partial mandibles and partial maxilla than we do, and isolated teeth than we do full skulls. And what I'll say is that to some degree, you can actually age isolated teeth too. And the reason you can do this is because of how we deposit enamel and how breast milks like impact on enamel and on development in general, as well as like there's this thing where like not sometimes, teeth in the crypt of the tooth, when they're still developing, don't have roots. They just look like a cap. And so you can also age an individual, because if you found an isolated tooth that's an adult tooth with no roots, you know that it belonged to an individual who hadn't erupted that tooth yet because it doesn't have any roots. They haven't developed. So even though you don't have the whole skeleton, you can say, okay, well, this tooth belonged to somebody who was under the age of 6, because this is a permanent molar. The topology of the permanent teeth look different than the topology of the baby teeth. You can say, okay, this is definitely an adult molar and it's got no roots, so it was still in the crypt. So whoever this tooth belonged to was under the age of whatever. You see what I mean?
Yeah.
That's how it works. That's how it works in forensic science too. So like if you find, like we do this exercise when I taught the lab, we would do this exercise where we would look at, like we have casts of like adult and then various levels of development for humans. So like if you were to find like a little piece of a femur, how would you age that femur just based off of what we know about human development, right? Or how would you age a tooth? You know what I mean?
Yeah.
Okay. Awesome. So only Homo sapiens, our species in particular, exhibits all of these characters that I just described in full, right? And we can examine big brains by looking at fossil skulls. We can examine the emergence of small canines by looking at fossil teeth. We can establish the broad dietary niche, so like what an animal ate, by looking at the isotopes, which are preserved in the tooth itself or in the sediment around the tooth if you're trying to reconstruct the environment. Microwear, so this is what one of my committee members does. Different foods leave permanent, or at least until like within a certain range, permanent scars on your teeth. So like if you spend all day eating nothing but popcorn kernels, I could take your tooth and put it into a micro CT scanner, and it will have all these little pits in it, right, from crushing those popcorn kernels. So you can actually like reconstruct diet to some degree, at least with soft versus hard versus tough foods, using microwear, as well as the shape of the teeth can tell you a lot about what something ate. Complicated tools, we find the tools at the fossil site. And extended time to maturity, you can use tooth eruption and microstructures of the teeth to tell the extended life history or lack thereof. So my conclusion here is that insofar in just this brief PowerPoint, like just a brief look at some hominins, we can see the emergence of all the characteristics that make humans human through the fossil record, right? Which is, unless there's another explanation to explain why we see mosaics of mosaics within each of these hominins, evidence for human evolution. I don't think creationists can sort these skulls, right? Like, I don't think I could give any creationist from David Menton to Todd Wood a cranium from a hominin and reliably have them sort it into this is a human and this is not. I don't think it can be done. And that's because there's too much variation within all of these species, because these species are all related to one another. So you can see them front to back or side by side. Like I always ask creationists, like, where's the line and why is it drawn there? So to me, and I'd love to get into, that's all I have. And so to me, what I would love is to hear, you know, from your perspective, if that's not evidence for evolution, I don't know what is. Like this is we're talking about dozens, plural, of species across thousands of specimens, some of which are partial skeletons that are found still in an articulation with one another.
Sorry, I didn't know I was on mute. No, actually, I grant this as evidence for evolution. So
Woo!
Thank you for sharing this. But like I said, I would still say this is like you said, this is a prediction that evolution made. Okay, so they said if humans evolved from apes, so we would expect to find such and such. And then we found things that can fit into that, right? And so I totally grant that as a evidence in favor of evolution. At the same time, I'm sure you recognize that I still have reservations about how much that actually contributes as evidence, and so I guess I would just ask you, like, what is the mechanism that you're proposing? Because these are pretty big morphological changes, right?
Yeah.
So are you proposing that this happened through just natural genetic variation? Are you proposing this happened through mutation? What is your proposal for how these big morphological changes took place?
So it depends on the feature, right? Like for something like canine teeth, this is going to be like, that's not hard. It's not hard to get small canine teeth as long as the social pressure is there. Like I study, this is like my bread and butter. I could tell you all about this and bore everybody to death as to like how and why do canine teeth change in size? Because most primates aren't carnivores, right? They don't use their canine teeth to kill animals. They use them to beat the crap out of each other for access to mates or resources. Kind of like how deer or horned animals will use their antlers to fight. And so the answer to like, why do some animals or some primates have big canines and some have small canines, and why in some species are males and females both having big canines and in some males have bigger canines, is because it depends on their social system, right? If males are fighting way more than females, they're going to have bigger canines. And what's cool about this is we've watched this change in real time. My favorite example is this colobus monkey called Colobus goriza, where you can like look at their range. And in the South, males and females have, I can't remember if it was in the North or South, but in the North or South, males and females have very similar sized canine teeth. And in the other direction, males have way bigger canine teeth. And males have bigger canine teeth where they live in bigger groups. And they live in bigger groups because it's not as dry. And so males can are encountering each other more often. And so they fight more. So the males that have bigger canines have more kids and they pass that gene on to their sons. It's like super classic example. And you can see this in a lot of different primate species. So it's like something like that. I don't think that's controversial. You're not evolving a change in the structure. You're shrinking the canine teeth and losing the hominin complex. But there are more complicated things at play here too, right? Like getting a bigger brain is one thing, but what humans are doing with our brains, we're not just changing the size. There's a rewiring that seems to be going on there too. Like we're emphasizing certain areas that even though other apes have them, they're not as big or they're not as fleshed out or they're not wired in exactly the same way. I will say that a paper came out just 2 weeks ago that I'll put in the chat or I'll comment it, one or the other, that was specifically on the pelvis, because that was a really big question. Like you saw the pictures of them side by side. A chimp pelvis and a human pelvis are like really different, right? Even though we can both walk upright, they're horrible at it. And it's in part because they've got this pelvis that can't anchor very strong muscles. It makes their pelvic floor weak. And their glutes are nothing to, I mean, they don't have any glutes at all. I mean, they do, but they're really small. And so the researchers asked this question, like, okay, how do you get a human pelvis from a chimp pelvis, right? Like genetically, what switches have to change to get that to happen? And in this paper, again, it just came out. It's a tour de force. I just finished scripting my video for it yesterday morning. But the researchers in this massive team found the specific genes responsible for taking the chimpanzee growth plate of the ilium and rotating it perpendicularly instead of in parallel, so about by 90 degrees. So instead of tall and thin, it's short and wide. And it's like a handful of genetic switches that change. Now, they're really important switches, but you can tinker with a non-human ape pelvis and get a more human-like form. I think they looked specifically at chimps, marmosets, or it might have been galagos, some other type of non-catarrhine primate, and then rats, and then they looked at humans. And they used this insanely old or expansive, reaching really old data set where they had like all these stained slices from like preserves and like Belgium and stuff. It was crazy what they did here. But I'll link it to you and can take a look. And they're basically like, hey, here's the genetic basis for how you get a chimp, or in this case, Rudopithecus pelvis, to look like a human one. And it's not as complicated as you might think. It's something that like you can do these switches and change it. As for did it happen quick or did it happen slow, they offer two hypotheses. They're like, okay, either this is a pretty saltational jump that allowed these guys to have a decent advantage, or alternatively, each of these genes changed slowly over a period of about, what would that be, 2 million years, about, depending on if you're going from Sahelanthropus or not. I'll link it in the description. So those would be how these kinds of things happen. But like that needs to be done for all of the major human changes. Like that's something that I'm really looking forward to. Like the fact that they were able to say, okay, human pelvis looks like this, chimp pelvis looks like this. How do we get one to look like the other? And then they have to go in and investigate the specific genes. I mean, the reason they didn't do this earlier is because the technology has never been better, but it's like the amount of work that went into this paper is just obscene. That would be my answer to that question. Large and small scale genetic changes depending on the structure in question.
Okay, so mutations, like genetic mutations.
Yeah, genetic mutations and social and environmental selection.
Okay. All right. Well, thank you so much for sharing your evidence. And I wanted to see, is there anything else? Oh, I wanted to ask about time, because you talked about over time.
Yes.
And so I wanted to kind of ask, because you showed quite a few species up there, or, quite a few specimens up there.
Yes.
How are they dating all of those? I know some can be dated with, volcanic ash, but how are you knowing what the how to label them as far as millions of years?
Yeah, so usually it's radiometric dating, like you were just talking about. You date the tuffs, and the nice thing about Eastern Africa is that it was like prone to volcanic eruption during the Miocene, Pliocene, and Pleistocene. And so what ended up happening is that I think we talked about this a long time ago, but I can't remember what we actually talked about. So if you're interested, maybe I went in detail in that. I can't remember what all we discussed, but like if you have a fossil, let's say there's a volcanic eruption, right? And in volcanic eruptions, it spews all this ejecta into the atmosphere, and it's got all these like microscopic igneous rocks in there that end up inside the ash. That ash layer gets laid down everywhere, and then it gets covered up again. Then I'm an Australopithecus. I'm walking around and I get killed by a crocodile and eaten. right? And I'm dead. And then my fossil is there. And then maybe 100 years later, there's another volcanic eruption. What you can do to get the date for that fossil is you can date the material either directly below, or the material directly below and directly above it, and you'll get an age range. Now, that's not how you do it for every single fossil, which is why sometimes you'll see, okay, they're dating volcanic tuffs and you'll get a range, versus sometimes they'll be unbelievably precise. Like at Dmanisi, I think they were able to say like 1.86 or something like that million years ago. And usually that's because they have a better material to radiometrically date there, right? So they'll have something like something that they'll be able to directly potassium argon date, or rather argon date, to get like a more precise figure. Occasionally too, I think depending on the type of fossil, there are rare cases when you can date the fossil itself. And then for younger stuff, you can do radiocarbon dating.
Okay. And so, and then that kind of brings me to one of my objections. So I want to see how you would respond to this, because what I've noticed is when I read about this, the dates change pretty frequently, and sometimes they change by millions of years. So like, what if we're dating these, and you said a range, but if we're able to move them around by millions of years, then how can we be confident that this is actually a progression over time?
I think that's an awesome question. I mean, so one of the ways that you can confirm, right, that the original date was like well-founded or not, because like, yes, dates do change for some of these fossils. But what I will say is the dates don't ever change, at least that I've seen, for hominin fossils, in part because East Africa is pretty easy to get dates for. South Africa is a different story. South Africa is a lot harder because the volcanism of Eastern Africa didn't reach down there. And so you have to rely on dating in these limestone karstic caves, and it's like a total nightmare. But in Eastern Africa, it's quite easy because of the reliability of these volcanic eruptions. When you see dates that have changed, they weren't confident in the first place, right? Like I can't, maybe I'm wrong, like maybe I've missed it, but I've not seen an example of like somebody coming out and saying like, okay, here's the date for the fossil, and like we're really sure, and then that ends up getting flipped on its head. And the way that I know the reason why this happens, and I'll tell you point blank because I've been there for it, right? Like at my site, at the site that I go, I always say my site because it's the site that I go to, but in Western Kenya, right on the coast of Lake Victoria, there's an area called Koru, which is where I do my work on Miocene apes, and the field site that I visited. Our geologist who was out there was having a ton of trouble with some of our sites and no trouble at all with others because of how these layers not just deposit, but then are eroded away later. So for some of them, he'd be like, we have a great sample. The sample of ash sediment is like really, really robust. We can send it off. We know that it's all coming from the same time. We're good. And then you won't get any error. Like the error will be really small in what returns. Whereas for some of them, he's like, this is going to be a hard one to date because the layer might be really fine. And so you might be worried about pulling sediment from below or above, or like maybe you can't guarantee that it's from the specific area. But because I was curious, because I do what I do, I asked him, I was like, are you guys like clear about that? He goes, oh, if we're like for sure not sure that this is from the same site, we won't send it off at all. And if we're doubtful at all, it makes it into the paper. So you'll know, like for some of these, some of the redates that came out for STS, I think it's STS5, the Mrs. Ples specimen, Australopithecus africanus, that got a date revision. South Africa, just like it always is, those South African fossils are the ones that are always prone to redating. And you'll find that the earlier versions of the publications were like, here's how we did it. Here's what we think the age range is, but that range is a fat range. That would be, if you're trying to figure out like, okay, how sure are they? They're, at least in my experience with the geologists that I know and the papers that I've read, it's pretty clear in the paper.
Awesome. Thanks. Did you want to share anything else?
I am trying to find that sample size for you right now for those Homo erectus individuals. Okay, red data, blue data, and where's green?
While you're looking for that, I'll just say, I titled this Evolutionists, Your Evidence Sucks. And tonight, your evidence didn't suck. Okay.
Woohoo!
I would say Erika actually brought a legit piece of evidence. And so good on you. And so
Give myself a pat on the back.
and so anyway, that's all I wanted to say. And I may even have to change the name of this. I don't know. I probably
No,
won't.
keep
I'll
it.
just leave
It's sexy. More people
All
will click
right.
on it.
All right, I'll leave it.
Okay,
So, well,
Rebecca,
maybe I needed to keep titling it that so I can keep, drawing the big fish over here to shoot me down. But okay, did you find it?
yes. So I'm going to put the link in the description so that you can find it. So for the figure with the red and the blue and the green, let me make sure that I'm getting my sample with the species correct here. Hold on, I'm just pulling it up. Because it wasn't as many as I expected. It was 8 instead of 12 for that figure that I gave you. Figure 3. I'm actually kind of giving myself a pat on the back though. I feel like that's a good estimate for what I was expecting. Okay, green. Let me make sure here. Nope. 8 is for chimpanzees. What is blue? Blue is also 8. 8 for all of them. 8 for all of them for comparison. Let's see. For the humans, it was 3 samples of finished children, red data from the Havako, green data from the Nostromo, 8 stage. You're just going to have to go through this. This seems to be what I'm looking for, though. It's underneath the figure. I'll put that.
And what did you find for the humans or for the Homo erectus?
Yeah, that's also 8. 8 for all of them. 8.
Oh, 8. Okay.
Sample of 8 for all of them. And then I'm going to put in here too your hip bone, the hip bone paper, bipedalism in 2 steps. I'm
posting this in the comments right now, and then I'll post it in the description after this so people can find it later.
There are your 2 papers. They're both pretty cool. I'll warn you, the bipedalism in 2-step one, there's so much genetics talk in there that I had to stop myself a lot and be like, okay, how exactly what are they saying here? I had to look up what heterotopic meant. It just means in an abnormal place. Heterotopic.
Okay. Yeah. Awesome. Well, thanks everybody. I appreciate the audience being here, and we had a couple of evolutionary biologists watching. So thank you, Dr. Dan and Dr. Joel Duff for being here, and for all who watched. Appreciate you guys. Have a great night, and keep making your evidence for evolution not suck. All right. Thanks.